Hello, good afternoon. Do you hear us? Good. Hello,
Hello.
good afternoon. Good Mitesh. Okay, so our speaker doesn't have more than 1 hour to be with us because he has another lecture. So I will start this session for today. Okay, so good afternoon, everyone. Welcome to the fourth webinar. Is about machine learning, and the title is "Revealed the driving force behind the artificial intelligence." Um, this webinar is designed to complement and to enhance with more experience and example of machine learning algorithm and project or application. So thank you for taking the time to participate to this series, and your engagement to reading the online chapter is very important to build the connection between the online chapter and the online webinar. So we look forward to your engagement and your continued engagement. And this is very important to be able to pass the test. So let me introduce our speaker. Is Professor Luis Liva. He is a professor of computer science at the University of Luxembourg, where he leads the computational interaction research group. His research interests lie at the intersection of human-computer interaction and machine learning. He is a professional member of the Association for Computer Machinery and the European Lab for Learning and Intelligent Systems. He currently serves as an associate editor for the International Journal of Human-Computer Study and the Machine Learning with Application Journal, LCVA. So before we begin, I would like to remind you that our speaker will spend 45 minutes to give the talk, with 15 minutes or less than 15 minutes to answer your question. So please, you can post your question in the chat section, and yeah, the recording will be available for those who want to rewatch the webinar or for those who can't attend us. So we are honored to be with us, Professor Luis Liva. I will give you the floor to start your presentation. Thank you so much.
Okay, thank you very much for the introduction. So this lecture will be about machine learning fundamentals, and this is the agenda for today. So we are going to learn some key concepts and definitions of machine learning. Then I'm going to describe a few learning paradigms, the three most important ones. Then we will see some applications, some learning algorithms with interactive demos that I hope that you will like. And then we will finish this talk with the final block, which is about challenges, current challenges in machine learning. So I hope that you like this schedule. So let's start with fundamentals of machine learning. First of all, as you might know, so machine learning is part of AI. And what is AI in the first place? So AI is the approach of trying to create machines that can simulate human behavior. Now, there are many approaches to this. We can use expert systems, we can use ontologies, we can use heuristics, and we can use machine learning. So machine learning is as part of AI, as I said. And the main idea is that machine learning will automatically learn from data without explicit programming. And I will emphasize on this last part of the sentence because this is the key differentiating factor of machine learning. We are not going to explicitly program a machine. So the machine will learn from data the desired behavior based on examples. Based on inputs and outputs, we are going to find a function that will map the inputs and the outputs. And I will show you some example later, no worries. Then I would say that nowadays, when people talk about machine learning, they are actually referring to deep learning. But deep learning is not, it's just machine learning with neural networks. And today we are not going to cover that part. But I have to say that this is my specialization. So my research expertise is mostly on deep learning models, which is, as I say, is just an instantiation of machine learning using neural networks. So all the concepts that we are going to see today are for, let's say, classic machine learning approaches, but basically you can then advance to the next session of this course about deep learning by understanding what we are going to cover today. So let's start with an example. You can find, this slide should be available to you. If not, please let me know. You can click on the links to get more insights about the example that I'm going to go over today. So let's take this, for instance, we have a machine learner. This is these robots here. And then we have some cats in this case, or somebody, is going to show examples, okay? So you see here, this is a fork. Got it? Okay, yes, I got it. This is a fork. Okay, now what is this? I'm going to show you another thing. So, okay, the machine learner is going to predict based on all the data, all the information, and all the evidence that has been provided by the cat in this case, then the machine learning is 100% sure or confident that this is a fork. Okay, but this is wrong, right? So the idea is that we are going to show examples, but then our engineer is going to say, hey, wait, I think I can do this myself in a much better way, in a much more efficient way. So they say, if the thing that I'm being shown is stainless steel, or the thing is made of wood, and the thing has 4 times, or the thing has 3 times, then this is going to be a fork, and else it's going to be something else. Okay, so the cat say, fair enough, but now let's try to do this for every kind of fork in the world. Try to write code that can describe plastic forks, antique forks, 2-time forks, 5-time forks, giant forks, glass fork, etc. And then the engineer say, okay, I have to write out all the possible characteristics that make something a fork. I need to define myself the forkiness concept. And this is so super hard. Unless you are a true expert in the task, most likely you are not going to come up with all possible features or characteristics of the underlying concept that you would like to model. And this is exactly where machine learning is excellent. So basically, if you can provide examples of things, here, pull for labeled data, and then the machine learning is happy because then it's going to be confronted with a lot of examples that can describe many objects and then can learn from the labels. Basically, this thing is a fork, this is a cup, this thing is a glass, whatever. So then now, based on the evidence that has been provided to the machine learner, then can you guess what is this, buddy? And then say, okay, I'm 93.4% sure that this is a fork, based on all the data and all the labels that were provided to me here. So that's the main point of machine learning. So basically, you don't need to write this kind of code. That's why we say machine learning is learning from data without explicit programming. This is explicit programming. So you need to declare the behavior of the computer and write all the rules, in this case, all the classification rules that will produce some type of output. With machine learning, we can learn from examples. Okay, we can fit a function, and we will see that there are many types of functions that we can use. We want to fit a function to a data set, a set of inputs and outputs. And machine learning is really, really good at this. Okay. So it doesn't matter if we are talking about, let's say, classification, not trying to put things apart, or if we are wondering about regression, trying to find some tendency in the data. It doesn't matter the problem itself. The key concept is that machine learning will start with a hypothesis. And then some hypotheses will be correct, other hypotheses will prove wrong. And the goal is that the computer will adjust the hypothesis, and it will try to learn from experience, from the examples. So let's see, for instance, we are going to establish a model, and the model, imagine, is something that has some knobs, so we can control some parameters of the model, and then we are going to send to make a hypothesis. So the model will say, okay, based on this current tuning of my knobs, what we call hyperparameters, based on these parameters that I have currently, I'm going to emit a hypothesis. No, this thing is a fork, or this thing is a glass. Then this is what we say here, a best guess will pop out, and then the model will be confronted by the size and shape of its error. That means sometimes it might get the hypothesis right. No, maybe if this input is something that looks like a fork and the output is a textual label, or this is a fork, then you are doing right. So maybe this knob here and this knob here and this knob here, they are well positioned. But if it's not a fork, if it's a glass or a cup of tea, whatever, then you need to change these knobs and put it in a different angle. Now, how do we turn these knobs to this angle or this angle? So this is precisely a function of the magnitude of the error. Okay, if we are very, let's say, off from the right label, we need to turn this knob a lot, let's say, to the other position. But if we are closer, let's say by a small margin, then we might need to fine-tune to move this knob slightly. And then if we can visualize the problem, I mean, this is very simple. This is called convex optimization. Basically, imagine that we have an optimum set of parameters. We want to approach this optimum. So basically, we start here. Okay, our model at the beginning has not very much, I mean, it doesn't know too much about the data set. So we are here, and then we want to approximate this optimum, okay? So basically, we are going to find the knobs, I mean, the position of these knobs that is optimal, okay? So we say that we are going to send our hypothesis forward. So we are going to emit something that might be right or wrong. And then based on the magnitude of the error, we are going to backpropagate the information to help the system retune those parameters. So the idea is that every time that we iterate over the data, we are going to be making better and better predictions. Okay, so we are getting closer to this optimum. Okay, and this optimum here means that this is the best possible combination of all the knobs, all the parameters of the model that are decided based on the inputs and the outputs, based on the examples. And as you can see, I mean, this is great because you can scale this up to millions of knobs. So every knob can be responsible for adjusting a given feature of the input. Okay, we will see later what can we do with these features. But I think I have convinced you that this is way, way more scalable than explicitly having to program the behavior of the computer. So we can basically provide examples, and we are going to fit a function, which is a model. The function is parameterized by some knobs, and we are going to find the best way of turning these knobs in some positions. Now, what things that we can do now with machine learning? I think basically we can distinguish between two big kinds of problems. One is discriminative modeling, and another is generative modeling. In discriminative modeling, basically we learn class boundaries. What does it mean? That we can learn to separate data or to find the best trending line, let's say, that will explain some data. In generative modeling, we are going to learn about the process that is going to generate the data. So we are going to talk about probability distributions, and this is a bit out of the scope of this talk. But just to let you know that when you learn more in your machine learning journey, you are going to, all the time, you are going to meet two kinds of problems. One kind of problem where you are going to, say, to discriminate data, another problem where you want to generate data. So, ChatGPT and all these large language models are actually doing something that we call generative modeling. And classification, regression is something that we will fit in discriminative modeling. So let's look at classification problems. So basically, you have a set of data, let's say documents, and we want to assign a class to this document. That's why classification. Now, if we are interested in finding some trend in the data, we have some like two features. Imagine 3D, it's like an extension, obvious extension of this. High dimensional examples are hard to plot, but for the sake of simplicity, let's think of two things like, I don't know, like the zip code of some neighborhoods in Luxembourg and then the price of the house. Might be some good correlation with that. So basically, in classification problems, we assign a label to each document. So here we have 1, 2, and 3 possible classes. Other document might remain unlabeled for whatever reason. But this is the classification problem. We basically are going to assign, let's say manually, or with the use of our robots. I will explain later what do we mean by this class assignment. And in regression, we are going to find, in this case, the best trending line that will explain the data. These are the two main kinds of problems that we are going to deal with in discriminative modeling. Either we want to assign labels to data, or we want to predict some continuous value, for instance, like a number, based on the zip code. I want to map a function that, based on the function on the zip code, I will produce a price, in the orders of millions of euros, whatever. Now I will introduce the learning paradigms. How can we accomplish this task? Like classifying things or producing some values as a result of a regression problem, or even how can we generate some data? So the first big learning paradigm that you should know about is called supervised learning, and it's basically the scenario where the labels are provided by a supervisor. And this can be a human or can be a robot. But the main characteristic of this learning scenario is that the labels are external to the data. So basically, we have some kind of data set. This could be whatever, sensor readings, documents, text, images, audio, whatever thing. Then we are going to assign labels using, I don't know, some kind of software, or even a human is going to sit in front of a computer. I'm going to say, okay, this example, this is a positive movie review. This example is a rock music audio sample, whatever. So we have somebody, doesn't need to be a human, could be a program, a software program, but somebody is going to assign labels to the data. Then we are going to put some algorithm to work, and it's called supervised learning, because we are going to assign a label to each piece of data, and then we are going to do something as the output. And the output can be, let's say, classification, can be regression. So we can assign, imagine that this is a classification problem, and we want to put each of these individual input samples, we want to put them into one of these three bins. So there will be a supervisor saying, this is bin number 1, this is bin number 2, this is bin number 3, and so on, for all the data. So as you can see, this is quite time-consuming and quite demanding, in terms of effort. Even if you have a robot, if you program a robot, like moving things around or trying to put some computer vision program to assign labels automatically, that still requires a lot of effort. So then we should mention the next big learning paradigm, which is unsupervised. Also nowadays called self-supervised learning. So unsupervised means that we don't have any supervisor. The labels are part of the data, actually. So we don't have anybody, neither a human, neither a robot, providing labels, that the labels are actually part of the data. So what does it mean? So we can take, for instance, we can check the structure of the data set. We can do clustering, we can try to put things together based on some similarity metric. We can, for instance, LLMs are trained based on this paradigm. So we can say, okay, I can download the whole Wikipedia in some language, and then I know that this sentence is a continuation of this sentence, and I know that this sentence is not part of this paragraph, or this sentence is not in this document. So all the data and all the labels are already there. So there is no need to provide any external labels. And again, once we select our desired algorithm, depending on the task that we want to do, of course, then we will process the data and we will do some output. It's also called self-supervised to emphasize on the fact that the labels are already part of the data. But usually, historically, it has been called unsupervised learning to make the differentiation with the fact that there are no labels external to the data set here, so that the labels are part of the data. And finally, we have the third big learning paradigm, which is called reinforcement learning. And basically, this is like, imagine that you have the same unsupervised or supervised model, but continuously interacting with the environment. Basically, the model is making prediction in real time. And basically, this is what we call agent, but this is like a program, actually a function, is going to produce some outputs that we call actions. on the environment, and then the agent will receive a reward based on the action that has been produced. And basically, this is a continuous loop. And this is, for instance, suitable. This this learning paradigm is suitable for real-time interaction, like finding how to navigate a labyrinth, like all action that require real-time interaction with some environment. Typically, robotics is the best paradigmatic example of reinforcement learning, but there are many more. Okay, now I'm going to introduce some learning algorithms that can implement supervised or unsupervised learning. I'm going to focus more on the supervised learning case because I think it's easier to understand, but you can, the idea is that in unsupervised learning cases, basically the labels are part of the data. I will show you an unsupervised learning at least, but you will see that for supervised learning, it's very easy to understand. For instance, the big or the most popular learning algorithm, a classic machine learning algorithm, is a decision tree. So basically, you have a data set, and the idea is to split this data set, try to classify your instances based on some properties. And basically, the decision tree is going to do a hierarchical partitioning of the data set. So we start with some number of leaves that we know, based on some discriminative feature, like if petal width is greater than 0.5, then we are going to put apart 6 gray leaves and then everything else. Now, if we go to the everything else part, now we are going to use the petal height, for instance, and then we are able to discriminate the remaining part of the data set into, let's say, 2 subsets. And then we can keep doing this division over and over until we are satisfied or until we cannot find any more splits of the data. And this is one of the most popular algorithms in classic machine learning, because this is very understandable. Let's say you can find some discrimination. It's like thinking of drawing some boundaries and then trying to find the best way of putting apart, in this case, 2 classes. Your data set will be split into subsets until there is no way to keep splitting the data. Of course, these decision trees can become very complex. For instance, you can start here and say, okay, based on the marital status or the education, I'm going to split the data in 2 parts. It doesn't need to be 2 parts, it could be 3 or more. Let's say based on this property, we split into 2, into 2, into 2, and now into 3, you see here. Based on this feature, we're going to split into 3, then this one will become a leaf node. So this could be a decision node. We can decide to classify or to do something with the data. So basically, we start here in the root node, and then we are going to find ways of navigating the data sets, based on the interesting features that we have decided. Okay, so now, as you might be guessing now, coming up with the right features to tell the data apart is a critical step. And this is something that machine learning is not going to solve. I will go through this later. This is something that neural networks can do very well, but we are not going to cover neural networks today. So another very popular approach is the support vector machine. Okay, this algorithm basically will try to find the best possible discriminative plane, let's say. This is a plane, but it's a line. In 2D, in 3D, it's a plane. And in more than 3 dimensions, it's called a hyperplane. The idea is to be able to discriminate the data in the optimal way. And basically, it's called support vector machine because we are going to find critical points that we call the support vectors that are going to tell us what is the best possible way to put them apart. So this red line, in this case, a line, because we are talking about a 2-dimensional case, is the best possible way of dividing these 2 groups of data. Actually, if you look at this distribution, so the green distribution like this and the blue distribution like this, there are many lines. So I can put even a vertical line should be enough to tell them apart. Any line that goes like this would be suitable. But the optimal line is this line here. And the support vector machine is an algorithm that will find this optimum, the best possible way of discriminating the data. Supervised machine, they also do something like really, really interesting, which is they apply some kernels, some functions that will try to discriminate the data in higher dimensions. For instance, if our data set is like this, it is impossible to find a line to tell these two classes apart. It's not possible using two features. Now, if we convert this space in a three-dimensional space, we can apply some tricks, no, and pretend that this has something to do with elevation. Then we can have a three-dimensional representation of the same data. Now we can put a plane. You see here? And this is precisely what the SVMs are going to do. So they no longer are going to find the optimal hyperplane in any dimension, but they also try to apply some different representations of the data. And these representations are basically transformations that the algorithm will do. Of course, if you have access to the slides, I think you can follow in more detail in these links to get to know more. This one is an example of unsupervised learning, and I have an interactive demo. I think it's better that we can go together through it. So basically, imagine I have a group of points. I'm going to put something like this, something like this. So maybe for a human, it's kind of clear, no? This is one group, this is another group. But for a machine, we don't know. A machine will start at some point, let's say here. Let's put manually. A machine can say, okay, there is something here. I think there is something here. Now, this algorithm for doing clustering is going to try now to assign a label based on what we call centroids, which is like the representatives. No? So we know in this data set that we want to find two classes. So, okay, let's see how the algorithm works. So we started some random points. It could be a point belonging to the data set, but I'm going to start with something outside as for an example, let's say. And when I'm going to go through the first step, which is based on this initial configuration, it's a random position, I'm going to assign a label. Okay, now the second step is to update the position of the representatives. No, when I'm going to do this update, then this is the average of all these groups. Now, if I keep doing this, now I'm going to look this, I'm going to run this for every half a second. Then the centroids are going to change the position at some point and it will stop. So in this case, it was easy. We started in an optimal configuration. Now let's see what happens if we add randomly 100 data points. And this is closer to reality. In reality, we don't have so clear differentiation. No? Let's say here I want to find 5 classes. And I don't know, because this is called k-means, because k is a user-provided parameter. So I'm going to add randomly 5 things, and I'm going to run everything. So this algorithm will reassign the label based on the minimum distance between centroids. And at this point, the algorithm has converged. So basically, this is our configuration. This is how we were able to find common clusters within a dataset. Now, if we say that we want to find 6, now we repeat, and now the algorithm will do the same steps and will reassign, or will assign a color based on the best distance based on each centroid. So this is, for the given dataset, this is the best way of grouping the data based on 6 classes, on 6K, let's say. And it's unsupervised because I didn't have to tell the algorithm that this is class A or class B. So I basically started from something completely random and say, okay, this is my data set. Now find the, let's say, 2 best possible allocations of the data. You see, even if I start here, the algorithm will reassign quickly the labels based on the best representative. No? It's trying to find what is the center of mass, the centroid of each of groups. So basically, this is the best way of dividing this data set in 2 classes. Now, this is the best way of doing it in 3 classes. Even if you start at a random point, you can see it's quite interesting how the algorithm will find automatically, the best structure of the data. Okay, so let's come back to the main presentation. Another interesting application in machine learning is called dimensionality reduction. Basically, we're going to deal with more than 2 and 3 dimensions typically, no? Because every dimension is going to explain your data in a way. Think of a predictive model for house prices in Luxembourg. You might want to put the zip code, the square meters, number of bedrooms, whether sunlight will be, the building is oriented to the north or south and so on. So you can define hundreds of features, and it's very, very difficult to visualize a high dimensional space because we humans, we can only visualize 3 dimensions. More than that, it's really hard. You need to invent like adding colors as a 4 dimension and adding hints. So dimensionality reduction is an algorithm that will project your data, your high dimensional data, into a low dimensional representation, typically 2D, I would say. If you start with a dataset like this, no, I don't know, 3D, then you have some representation like this, but then you can project in 2 dimensions or even in 1 dimension. It depends on your application. And this is something that machine learning can do actually very well. And this is another example of unsupervised learning. We can take, for instance, 2 axes and say, okay, let's see how variable is the data in 2 dimensions. And then you compute what we call the variance of the data. And then you will be able to project the data based on the amount of variance computed. And this is an example of one unsupervised learning algorithm that is very useful and widely used for plotting high dimensional data. Try to understand the latent structure of your data to see how high dimensional data set can be visualized in 2D. Okay, I think we are approaching the last part of this talk, which is great because we have approximately 50 minutes and I have a few demos here that I would like to show you. This is about the challenges in machine learning. First of all, we need to think of the quality. And we'll come back to this concept later on. But basically, we need to think about the volume of the data, the variability of the data, and the velocity at which we can collect the data. So for instance, how much data is available, no? The volume. Are we talking about megabytes of data, gigabytes of data, terabytes, petabytes, etc.? Because depending on the scale of the data set, we might need to apply different algorithms for preprocessing and learning. Then the velocity, how frequently does the data arrive? Are we talking about a data set that is already collected offline, let's say, like a collection of images, or is something that we are getting in batches? No? Like today we get 100 images, tomorrow we get 20, past tomorrow we have 50, and so on. Or is it a stream, let's say real time? No, we are receiving data from a robot arm, and then we are receiving X, Y, and Z coordinates at every millisecond. So this is different. No? The velocity of a stream dataset is, of course, many orders of magnitude larger than offline or batch-based data. And another thing is that near real time, for instance, in geographical information systems, they consider real time if you can collect satellite data from one day to another. So from one day to another is considered real time in geographic information system. So we can think of near real time applications based on this velocity of the data. And finally, we have to think about how variable is data. Are we talking about structured data, for instance, something that we can put as a table, for instance, or is something unstructured, like free-form text? No, it's hard to parse, no, to compute, put in a mathematical form, let's say. Is it multimodal? Are we dealing with text only, or a combination of text, images, audio, and so on? Is the data private or sensible? Because, for instance, it turns out that clinical data is super private and sensible, but it's also highly variable. It depends a lot on the individual. So unless we can collect a lot of data that is representative of the population that we want to model, then, our learning algorithms might fail. So we need to think about these 3. All the people in big data, they mention a 4th V, which is veracity, like how truthful is the information. But these 3 Vs are the essential ones that you need to know. Some examples of, let's say, medium, low, or high volume variability or velocity. Let's think about the traffic cameras, for instance. I would say medium volume because there are not infinite cars passing through a camera. I would say medium velocity. Cars can go, let's say, between, depending on highway, between, let's say, 80 and 120 kilometers per hour. And the variability should be low, as in how many car brands are there, maybe hundreds. We're not talking about millions of different cars brands. Of course, this classification might be subjective. These are examples that I'm just giving you to illustrate what could be high, low, or medium volume variability or velocity. Let's think about search engine logs from Google, from Bing, and so on. So this is high volume. So people are, I think the number of queries that Google search is receiving every day, per second is close to 50 million, if I'm not mistaken. So 50 million data points that will go to Google servers per second. The velocity is also, per second is quite high. And variability, can you imagine? So people can type whatever on a search engine. So this is an example of high volume, high velocity, high variability. Now, if we talk about clinical data, think about, like handwritten data that people use in neurology to assess Parkinson's disease, for instance, from handwritten drawings. This could be considered low volume because it's really hard to recruit patients and to invite them to the hospital and do some screening tests. So it's low volume. You are not going to see, let's say, more than 20 patients per day. The velocity of the data is also slow because you are not going to collect more than one or two drawings. And the variability, because we are talking about one or two neurological tests, then the variability of the data should be medium. People might have variability, let's say people with or without Parkinson, they might have differences that are clear, but there is not much variability in the sense that we are only administering one or two tests. And of course, this classification, as I say, might be subjective. Just to give you an example, this is the kind of problems that we are modeling with machine learning nowadays. So another challenge that I have to mention, and I think that you might guess, is if we provide garbage to the model, we are going to get garbage as an output. This is called the garbage in, garbage out paradigm. So it's very important to preprocess the input data, have clean data, or at least have data that doesn't contradict the labels. If you show some fork, and you say this is a steel fork, and then you show a car and you say this is also a fork, then you are telling the machine learning model contradictory information, because the features that are going to represent two different objects should not have the same label in this example. And I have to mention the feature engineering part is very, very, very challenging. And I'm going to illustrate that in this pipeline. This is the typical machine learning pipeline. So we are going to get some recording from the real world using some sensor, whatever it is. A sensor can be a camera, a sensor can be a pen, whatever. So we are going to convert the real world into a mathematical representation. So we are going to, let's say, if it's a picture of a traffic plate, we most likely are going to apply some kind of brightness or contrast preprocessing. We are going to isolate digits and so on, and then we are going to decide what are the best characteristics that will define the input data. Then if we do this right, everything else will follow. Everything else means that we can classify, we can decide to find similar objects, we can try to predict a variable, like a continuous variable. But if we don't get this part right, everything else will not work. And this is the classic and most long-standing problem in machine learning, that we need to decide what are the best features to describe our data. So I'm going to highlight this because it's super important. Imagine the problem of finding out the price of a house in Luxembourg. So we can say, okay, I have a data set and I'm going to put, let's say, a long sequence of values, and the first value in this sequence is the zip code. The second value in this sequence is the color of the walls. The third value is the number of windows. So you see the color of the wall might not be a very good feature. So I might be introducing noise to the model. If I'm going to map all these input variables with an output variable, in this case, it could be the price of the house. If we are going to put irrelevant features or features that are not going to have a strong discriminative power, this is not going to work. And this is one of the big problems in machine learning, that we need to decide what are the best features. There are algorithms to decide that, help us deciding that, but we need to, as an expert, let's say, as a domain expert, we need to establish what are the potential features that will somehow characterize the data. This is the part that neural networks are doing automatically. But in classic machine learning, for like decision trees, SVMs, and so on, we need to put the features ourselves. Another challenge is the model evaluation, and I will show you a nice interactive demo. So basically, when we collect some data, we need to create 3 splits. So one for training the model, another one for validating the model, and another one which will be like a held out partition. It's something that we will never see during training, which is called the testing set. And this is, let's say, a proxy of real world data. Basically, so imagine we want to classify cats and dogs based on 2 features, the weight of the animal and the fluffiness of the animal. So we are going to create 3 partitions. Again, we are going to fine-tune, we are going to find the best position of the knobs of our model based on this data, and we are going to validate how good are these knobs positioned against this data set. And once we repeat this part of fine-tuning, moving the knobs and evaluating, then after some time, we say our model is ready. Now let's go to the real world and test the model. This is how we are going to operate. And you can see that here, okay, we are going to decide how to put our features. Let's say if I don't use anything, I'm going to use a majority vote. Okay, so based on our data, I have more cats than dogs. Okay, I'm going to predict that whatever comes in is going to be classified as a cat. As you can imagine, this is a random classifier. This has no discriminative power at all. Now, if we put the data by weight, okay, we can see that overall cats are lighter. In terms of fluffiness, there should be, okay, cats are typically fluffier than dogs. If we put both together, now we can see, okay, some line that can discriminate. But wait, this is based on the training data. Now, if we go to the validation set, now we see, we are collecting more evidence of our real world. And now we see that we have cats at both sides of this line. So that's why we need to change the slope, in this case, of this line. And we can keep doing this for several iterations until we go to the training set. And this is the final step. Once we decided already all the knobs and all the parameters of our model, we are going to evaluate on the real world proxy, which is a test set. So basically, with this example, I want to emphasize how important it is to split the data. Imagine that you put only cats during training. Then your model has only information about cats. It's not going to produce any output related to dogs at all. So it's important that you can split your data set in a way that is representative of the real world, and also that the data set that you're collecting is representative of the real world too. Okay, and then finally, this is also connected to the concept of overfitting, that either you might end up with a too simple model or a too complex model. Okay, go quickly through this. Again, you can play with these animations then at home at your own pace. Basically, imagine model is too simple. We can split the data in 2 parts. There will be some misclassifications. It might be a good feature, but not enough. Okay, so there's some error. Now we can keep splitting the data. The year. I mean, this is an example of houses as well. So the year the house was built, the price per square meter, and so on. We can keep adding features up to the point where our model is completely isolating classes. But this is super complex. I mean, we are actually memorizing the training data. So basically, when we use the test data, which is a representative of the real world, we are going to have several mistakes. So this, this is connected to something called the bias-variance trade-off. I believe is a bit out of scope, this talk. But the idea is that we should not have very simple model or very complex model. If we go through different tasks, we can visualize this better. So if we optimize, by imagine we want to classify. Remember that the point in classification is to find the best discriminative boundary. We might end up into something like this. I mean, we are discriminating perfectly our training data, but then when we go to the test data, it might happen, like here we have a blue dot, in the test data, and then our model is actually not doing a good job. Our model is overfit, is actually memorizing the data. We don't want that. And the model can be underfit, which is too simple. We are using this line, which is not enough. So we just want something like this. This is the right fit. It's not too complex, not too simple. And we have to accept that in the real world, it's very hard to get something that is 100% accurate. It's almost impossible because the real world is messy, it's chaotic. We have to embrace this reality. And for regression, it's the same. Imagine that we want to fit a line perfectly to all single values, then actually we're not going to be able to extrapolate to real world data because the model is memorizing the data set. We don't want that. We want to find something that is just about this. Okay, so I think that's all. That concludes my talk, and now I'm happy to take your questions.
Do you hear me?
Yes.
Yeah. Thank you so much for the great presentation. It has a lot of details about different type of machine learning for classification, for clustering, and yes. Yeah, I think we have a lot of questions. Let's do our best to answer all of them. Okay, the first one. How the machine learning knows if the output it provides is wrong, if there is no code in which is mentioned the correct answer. So I tried to answer some of them in the chat, but I would like to your point of view.
So how does the model knows that some prediction is right or wrong? If we are talking about the supervised learning case, then you are going to have a label for that. So you basically, based on the data set that you can collect, then you have training data set or split, a validation subset, and test subset. So basically, you take the training data, and training data is always one input and one label. And then the model says, okay, for this input, it's like one example we saw the cat showing the fork to the robot. So you are going to iterate over the whole training data and say, okay, for this object, this is the label. For this object, this is the label. And then the model will change the knobs, will fine-tune the parameter, and you go through the validation subset of the data, and then you are going to confront the predictions or the hypothesis of the model against the label that you did not see, and the model did not see during training.
Thank you. Next question. Can you explain more this hypothesis is confronted by the size and shape of its error?
So basically, maybe we can go back. We're here.
But we don't see the slide because we are making the question.
Do you see my screen?
Really, can we see the slide again?
Maybe I can share again my screen.
Yes.
Let me check.
No, we see your slide, but the first one. Okay. No, it's fine.
Yes. So basically, this is the idea is that your model, based on the training data, is going to find some positions of these knobs, and then your model will say, okay, based on the training data, I found this position. Now I'm going to go through the validation data, and I'm going to emit a hypothesis. Okay, I'm looking at something that is made of steel, and it has 3 tines, so I'm going to say that it's a fork. Now, the size and shape of the error, in this case, the error is 0 because I got the prediction right. I say it's a fork, so the error is 0. Now let's think about something simpler, different based on the regression problem that predicting the price of a house. I say the price of this house based on this zip code and based on this number of bedrooms and based on this orientation is 800,000 euros. Now it actually is 900,000 euros. So my error is 100,000 euros. So next time I'm going to move the knobs so that I want next time I'm going to tell something that is closer to 900 and not 800. That's the goal of moving these knobs and confronting the model with the shape and the size and shape of the error.
Thank you. Next question. Can you suggest 1, 2, 3 books where to learn and go deep into that?
If it's, it depends on the viewpoints. If you are a practitioner, there are some books that might be, let's say, more applied. If you would like to see the mathematical principle, then there are other books. I would say for classic machine learning, the Bible is the Duda and Hart book. But this is only for mathematicians, let's say, and this used to be my reference textbook when I was doing my PhD. Now, if you want something more applied, there is a book called Machine Learning in Practice, where they even have Python codes. So in the book chapters.
Thank you. Another question. Do you not get very wrong output category when using unsupervised learning? Like, for example, you give the system song from hip hop, classical, and rock, but instead of the system categorizing them into this class, he will then categorize them, for example, into song over for minutes or 3 minutes and song under 3 minutes without looking at the chunk. What do you think?
But what's the question?
Can you read it? Can you see the question? Because we make
Well, it's really, I mean, there is a question tab here.
Question means is that instead of the algorithm using the genre of classical and rock, he can use other genre to classify, like take consideration the size, like 4 minutes, 3 minutes, and of 3 minutes. So instead of
Okay, yeah. So I mean, this is connected to the discussion that I mentioned about the features. Okay, so you can decide to classify a song based on the tempo, on the duration. No, I mean, even the genre, or the genre can be the label to predict. Of course, I mean, anything is possible. You need to put the data in let's say in a tabular format. These are my features, these are my outputs, and based on that, I mean, you can predict whatever you want. Anything that can be expressed in a numerical format will create something that we call the feature vector, and then the output could be a categorical label, could be a number, could be something. But your features should be something that you can measure. If you can measure something, then you can predict it. No problem.
Okay, thank you. Next question. The decision tree seemed to be like the example in the chapter about the life expectancy, like linked to the number of education year, isn't it?
Well, I mean, I took this example from a website, so I'm not endorsing the use case. Just an example, no? I mean, you can classify some data based on different, let's say, weak classifiers. No, we can start splitting by education or by occupation, by income, by productivity, education, work class, whatever. This is an example you can find in this blog post.
Yes.
Well, I put this slide just to illustrate the fact that when we talk about decision trees, we are talking about splitting our data into more fine-grained subsets. And it doesn't need to be binary, like most of the examples that you will find in textbooks. It could be like 3 or 4 or 5 different splits of each decision variable.
Yeah, exactly. Okay, are Hilbert space used in machine learning?
Yes, I mean, a Hilbert space is basically a representation of the data. As I said, I mean, anything that you can put in a numerical format is suitable for learning.
Okay, next question. What error rate is acceptable?
It depends on the application. I can tell you, for instance, in handwritten recognition, when you are using a digital pen and try to enter like calligraphic style, more than 5% is considered not usable for a human.
Yeah, exactly. It depends to the application, to the problem we want to solve, and to the impact of the error in the domain. Okay, next one. Can you please better explain k-means clustering?
K-means, so basically it's an algorithm that will find automatically the number of classes that you would like to find. So K is a user-defined parameter. So it's something that, in principle, I mean, you can try to find K automatically, but the algorithm is designed like, give me how many classes do you want to find, and I'm going to give you the best partitioning of the space. For instance, here we start here, and I want to find 3 clusters.
Yeah, it's
So
like you want to decide how many cluster and group you want to
how many
do
groups do you
your
want to
data.
find? And then the algorithm will try to find, based on 3 prototypes that you can start placing at random, is going to assign the category. No, here we are showing a color, but it could have been a number if we want to do something else. Basically, we start with 3 random points, and then these random points will become the representative of each class. So we need to reallocate them based on the minimum distance of each point to this representative that we call the centroid.
Okay, another question. Can the machine also suggest that some input could be error or falsely labeled?
We can have a model to try to predict the likelihood of a label. Yes, I mean it could be like a meta model. So you can first pre-train a model on some good quality dataset, and then use this model as a basis for labeling a dataset automatically. Yes.
Okay. I see more and more content talking about convergent learning as an automated deep learning process used by model to learn from big data and raw data, meaning the model itself process label and learn from data. Does it mean that for large model quality of data is less important?
Well, man, this is a good question. If there are a few outliers, then it doesn't matter. But if your dataset is full of bad examples, then it's not possible to produce a good model out of it.
Yeah, because the idea of convergent learning and how large model handle raw data is fascinating itself because it's not easy at all, but it's a bit also more nuanced when it comes to the quality of the data. So it's a little bit challenging. Okay, all database are based in voluntary data submission and or collecting data from provider or other source. What are your thoughts regarding Data Hub Center? Luxembourg has 9 of them. How trustful can be such a data center if used?
I mean, I think we have to go on a case by case basis. I don't know. I mean, you need to look at the provenance of the data, but in principle, if it's public and it has been validated through some publication or some study, I mean, I think it should be fine.
Okay, so it's time for our speaker to leave us because he has another lecture in other department. And yeah, sorry for that. Thank you so much, Professor Luis, for your time, for your
Yeah,
presentation. And
thank you for hosting me.
thank you. Thank you so much. So, dear participants, so dear Professor Luis, you can leave us and go to your lecture. Thank you so much for being with us.
See you.